Welcome back, Physics 30. This is the 33-4 General Relativity, Gravity and the Curvature of Space section. Before we look at this, we'll look at some forces that we see in nature. We see the nuclear forces, the forces that hold nuclei together in atoms. We also see magnetic forces, so a north and a south pole. We know that there is mutual attraction between there, but if we use like poles, north and north or south and south, there's repulsion. If we look at electrostatic forces, opposite charges attract, but if we have like charges such as negative and positive, there's repulsion. And then lastly, classic Newtonian gravitational forces, in which we have large bodies having a mutual attraction with each other, but the interesting thing there is there's no repulsive force. There's only attraction around extremely large bodies such as the Earth, or in fact any body exerts a force of attraction. So we have seen that the force of gravity plays an important role in the processes that occur in stars. Gravity too is important for the evolution of the universe as a whole. The reason gravity plays such a dominant role in the universe and not one of the other four forces that I mentioned is that gravity is exerted over a long range and it's always attractive. So that's an interesting thing. There's no repulsive force. So they talk about here the nuclear forces act only short distances, hence they don't act over astronomical distances like gravity does. Electromagnetic force, like gravity, acts over great distances but can be either attractive or repulsive. And since the universe does not seem to contain large areas of net charges, a large force does not exist. But gravity acts only as attractive force between all masses, whether they're Earth or smaller masses with smaller objects. And there are large accumulations of mass in the universe. The force of gravity, as Newton described in his universal law of gravitation, which we'll take later on in the course, was modified by Einstein in his general theory of relativity. Einstein developed a theory of gravity that now forms the basis of cosmological dynamics. So back when we took special theory of relativity, we concluded that there is no way for an observer to determine whether a given frame of reference is at rest or moving at constant velocity in a straight line. There's no experiment we can do to determine which one we're in. Thus, the law of physics must be the same in different inertial reference frames. But what about if we talk about situations and when we're accelerating? So when rocket ships decelerate or accelerate or turn directions. Einstein tackled this problem of accelerating reference frames in his general theory of relativity, and it also developed a theory of gravity, which is quite interesting. The mathematics of general relativity is complex, so we'll just look at qualitative concepts here. So first we look at Einstein's principle of equivalence, which states that you can't do an experiment that would distinguish between a gravity field and an equivalent uniform acceleration. And I just added here in the opposite direction, as we'll see. So gravity pulling down on an object would be equivalent to that object accelerating in the opposite direction. So the examples here we look at are a thought experiment of an elevator out in space. So if we look at that and see exactly what we mean by this. If observers sense that they were accelerating, as in a vehicle speeding around a sharp curve, they cannot prove by any experiment that in fact they weren't simply experiencing a pull of gravity in the opposite direction, as we'll see. Conversely, we might think we are being pulled by gravity when in fact we are undergoing an acceleration, which has nothing to do with gravity. As a thought experiment, consider a person in a freely falling elevator near the Earth's surface. If our observer held a book out in front and let it go, what would happen? The gravity would pull it down toward the Earth at the same rate at which the person in the elevator was falling. So here we're talking about an elevator in free fall. So if we pulled it up, cut the wire, you're accelerating down, and anything you hold out is accelerating it down at the same rate, and so that book would appear to be floating in midair. Just like similar when you see on TV or planes in free fall. So astronauts can see what it's like to be in a zero gravity environment. If everything is falling at g, the acceleration due to gravity, the plane and the contents inside, it's like having zero external forces on you. So according to the principle of equivalent, the observer could not determine whether the book fell because the elevator was accelerating upward or because gravitational field was acting downward. Actually, I skipped a part here. So the book would hover right next to the person's hand. The effect is exactly the same as if you had been no forces were acting and you're out in the middle of space. On the other hand, though, if the elevator was out in space where the gravitational field was zero, the released book would float just like this. But if the elevator was out in space and if we pulled it upwards, of course, everything here wants to stay at rest. Therefore, if you move the elevator up, you end up being pushed on the floor if you're accelerating upwards. So if you're accelerated upward at an acceleration of 9.8 meters per second squared, the book, as seen by the observer, would fall to the floor with an acceleration of 9.8, just as if gravity was operating in the opposite direction. So according to the principle of equivalence, the observer could not determine whether the book fell because the elevator was accelerating upwards or because there was a gravitational field pulling downwards. So that's interesting. Gravity on Earth pulls downwards, so we are on the floor. All objects fall on the floor. If you were out in space and if all of a sudden the elevator was pulled upwards, you, of course, an object at rest wants to stay at rest. Elevator's moving upwards, and you end up falling on the floor as if there was a gravitational field. So there's no way you can tell the difference between the two, whether it's gravity pulling down or whether you're accelerating upwards. And that's a key thing that happens here, and that has kind of a weird effect too coming up. We're going to skip this section here because we'll be talking about that when we look back at Newton's law and gravity. So we'll look at this other little experiment here involving a light beam across in an elevator, similarly to what we had in the spaceship earlier on. So the principle of equivalence can be shown to show that light ought to be deflected by a gravitational force due to a massive object, which is interesting. Consider another thought experiment in which an elevator is in free space where virtually no gravity acts. If a light beam is emitted by a flashlight attached to the side of an elevator, the beam, of course, goes right across and hits the other side. Okay, so straight across the elevator and makes a spot on the opposite side. If the elevator is at rest, or if it's moving at constant velocity, because the flashlight would be moving at constant velocity too. But if the elevator accelerated upwards, so sped up faster and faster and faster upwards, the light beam would travel across as if it were at rest, but since the elevator has already moved up, now we're talking again here, quick movements, extremely fast acceleration. By the time the light beam hit here, the elevator had already moved up a bit. By the time the light beam hits here, the elevator had moved up a bit. So the light beam is still going across straight, but since the elevator is accelerating upward, it looks like it gets deflected. Similarly to that 1960s video in which we have an accelerating cart, and instead of the ball falling straight down, it fell back in a curved fashion. Same thing here with the light beam. If it's accelerating upward, the beam looks like it gets deflected downwards. And that's interesting. So why? Because during the time that light travels from one side to the other, the elevator is moving upward at a vertical speed that is increasing relative to the light. Next, we note that according to the equivalence principle that we looked on the previous page, an upward accelerating reference frame is equal to a downward gravitational field. Hence, we can picture the curved path of light being bent due to accelerating upwards or being bent due to gravity pulling downwards. So that's so we expect gravity to exert a force on the beam of light and to bend it in a straight path. Because remember, there's no way to determine whether you're accelerating upwards or a gravitational field is pulling you downwards. So that's the interesting part. Gravity can bend light since it's equal and opposite to accelerating upwards. So that's kind of the interesting part of this section. And we'll stop it there and we'll look at this again in the next video.